ఫుల్ కొడాలి 2 రోజులు ఎండ రావద్దు చల్లగా ఉండాలి తర్వాత మళ్ళీ టేస్ట్ కొడుతుంది మళ్ళీ ఎండ గట్టిగా
Download me.
Good morning, one and all. Am I audible, ma?
Madam, good morning, madam.
Yeah.
You're audible, ma'am.
Yeah, thank you.
Ma'am, I made you co-host, ma'am.
Yeah. Yeah.
Once, just we'll wait for 5 minutes, ma'am.
Okay, ma, no problem.
I reduced my voice. Just keep in groups, no? Going.
Second year, sir. Good morning, everyone.
Good morning.
Chemistry. Dr. B. Sireesha, ma'am, Associate Professor of Chemistry, OU. Madam is going to deliver lecture on coordination compounds 2. Ma'am has completed MSc and PhD from Osmania University. She has 28 years of teaching experience at UG level and 25 years of teaching experience at PG level. She has 29 years of research experience and published 42 papers in national and international journals and presented 42 research papers in national and international symposium and seminars. So on her guidance, 5 research scholars were awarded PhD, 2 students submitted their research, and 5 students are still working for the PhD. Ma'am research interests us under biocoordination chemistry, spectroanalytical studies, crystallography, DNA binding and cleavage studies, computational studies.
Yeah, I think Anjum, we can stop
So
here.
ma'am has two minor projects. Yeah, ma'am, I can. Because those who are joined new, for them, I'm giving you a brief introduction.
Okay.
Ma'am has published books regarding as a co-author for 2 years government Telugu Academy BSc textbooks for chemistry semester 1, 2, 3, 4, and 5 for CBCS syllabus, both in English and Telugu medium, with 7 and 4 chapters in Telugu medium and 7 chapters in English medium. Ma'am has organized 5 national symposium, workshops, seminars, and attended 40 national and international conferences, workshops, seminars. She is a life member of Indian Chemical Society, Kolkata, Indian Association of Chemistry Teachers, Mumbai, Indian Association of Analytical Scientists, Mumbai, the National Society of Teachers and Researchers in Chemistry, Bhubaneswar, and the Indian Science Congress Association. I welcome you, ma'am, once again on behalf of Chemistry.
Yeah, thank you very much. So I request all the audience to mute yourself, or shall I take the lead of muting? Because if I mute yours, like if I take the option of not unmuting yourself, any questions asked, you may not be able to answer. And you can answer in the chat box, okay? So let me share the screen. If you all remember, in the last class, we have completed with the computational Is the screen visible?
Hi, yes, ma'am. Screen is visible.
Yeah. Okay. The last class, if you all remember, we have done with up to the valence bond theory of the coordination compounds. Just a brief 2-minute introduction, I'll be giving you what we have done in the last class. We have taken up the definition of the coordination compound. That is, coordination compound will exist both in solution and in the solid form. Once the coordination compound is formed, the metal ion and the ligands binding it, they lose their identity and they act as a single unit. Then many theories were put forward to explain the bonding between the metal and the ligand. So we have seen the Werner's coordination theory, and then we have seen the Sidgwick's EAN rule, and then valence bond theory. So we'll be continuing because of certain limitations in the valence bond theory. Again, further theories were put forward like crystal field theory and molecular orbital theory also. Here in the crystal field theory, it was given by Bethe in 1929. In this theory, in valence bond theory, the Pauling gave the postulate that all the ligands will be donating a lone pair of electrons into the empty orbitals of the metal ion, forming the coordinate covalent bond. Here, in the case of the crystal field theory, the Bethe has given the assumption that the metal ligand bonding will be purely of the electrostatic interactions between the metal ion and the ligands. Ligand, if it is neutral, the negative dipole end will be acting. That means the metal ion and the ligands were assumed to be the point charges, and the bonding between these two is assumed to be purely ionic in nature. And as we all know, the formation of the bonding, like the metal ligand bonding, as in the cases of the valence bond theory hybridization, we have seen the formation of the square planar complex, formation of the tetrahedron complex, formation of octahedron complex. We have taken few examples and we have studied. Now we will be taking up the examples here in the orbitals, how the ligands, when the ligands are approaching towards the metal ion, the d orbitals, the 5 d orbitals which were degenerate earlier, what changes they are occurring with these 5 ligands is delta. Okay. So you should have the knowledge of the shapes of the d orbitals. So these are the 5 d orbitals. They are named as dx square minus y square, dz square, dxy, dxz, and dyz. If you observe the shapes of the orbitals, the lobes of the first 2 orbitals, that is dx square and y square and dz square orbitals, their lobes are oriented along the Cartesian axis. Okay, if you see here, this is the x-axis, y-axis, and z-axis. In this case, the lobes are oriented along with the x and y-axis. In the case of the dxy, the positive lobes are oriented along the z-axis. Okay, whereas in the case of these 3 orbitals, the lobes are in between the Cartesian coordinates. Okay. So when there is no ligand field, when the ligands are not approaching in the free metal ion, all these 5d orbitals are degenerate in nature. But when the ligands are approaching, then depending on the spatial orientation of the ligand, the Bethe proposed that the d orbitals split into various energy levels. So let us see in the octahedron case. You all know the shape of the octahedron. Then we will try to place all these d orbitals in the octahedron and see how the ligands are approaching and how the which ligands or which orbitals are being affected in the approach of the ligands. So actually this will be the s orbital, which is the universally or totally, it is a non-degenerate and totally positive spherical lobe. Okay, so the ligands approaching along the direction in any direction from space, they will be having the same effect on this particular orbital. Now check this dz square orbital. The ligands which are approaching along the z axis will be affecting the electrons present in this particular d orbital. In the same way, in the dz square, the electrons approaching along the x and y plane will be affecting more or repelling the electrons of these metal ion present in these orbitals, and the electrons of the ligand will be repelling. Whereas if you see in the case of the DXY and the other three cases, the orbitals or the electrons are away from the electrons of the ligand. And he has labeled these two orbitals whose lobes are oriented as the EG orbitals. G, we are writing it as Garade. The D orbitals generally, because L, if you know the azimuthal quantum number 0, 2, 4, 6 and all, the orbitals will be S orbital, D, G and so on. Okay, the alternate, when L is equal to 0 or the even parity azimuthal quantum numbers, we will be writing the orbitals in terms of the G, that is Garade, symmetrical orbitals. They possess center of symmetry. Okay. So, and these three orbitals, they are named as T2G. Here, T stands for triply degenerate. Okay. And E stands for doubly degenerate. And this S orbital, we all know it is a non-degenerate orbital. It is unique. It is single orbital. The next we will see how the orbitals split. Now we all know that the two orbitals, that is the EG orbitals, undergo a different type of the repulsions when compared to the T2G orbitals. So these are the EG orbitals. These three are labeled as the T2G orbitals. Well, let us see the splitting pattern. Now the ligands are approaching to the central metal ion along the Cartesian coordinates in the octahedron geometry. So the splitting is, now the orbitals which are more affected are the EG orbitals. That means they are destabilized, and the orbitals which are like less affected are getting stabilized. The stabilization energy of the total of the orbitals here is about 2/5 of the 5 orbitals, and here it is 3/5. Okay, this is destabilization energy, and this is the barycenter, which where the energy is 0, and stabilizing means energy is getting lowered than 0. It is going, so we call it as minus. We see it in the form of negative sign. And here the energy is, this is the destabilization energy. And the total energy difference between these two levels, it is the delta O in octahedron state. And delta O will be equal to 10 dQ. And of the 10 dQ, 6 dQ is positive, and here 4 dQ is negative. Hence, this is the barycenter. And the repulsions in the octahedron will be yielding two energy levels, that is upper energy or the higher energy EG orbitals, and then the lower energy T2G orbitals. So this is the pattern of splitting. Textbooks will be giving you in between a hypothetical situation. That hypothetical situation is assumed thinking that all the ligands are approaching in the similar manner and the effect on all the orbitals will be same. Okay, so here I have avoided that hypothetical situation. The next we will see the splitting pattern in the tetrahedron geometry. So this is a tetrahedron. Here, if you draw a cube, then the ligands are present in the alternate corners of the cube, and the axes are passing through the center of the faces of the cube. Okay, so along the Cartesian axis now, the orbitals, that is EG orbitals, will be oriented. Now, to the edges, see the edges here where I am drawing the red line. Towards the edges, the lobes of the T2G orbitals will be lying. So these orbitals are actually neither directly coinciding nor they are like far away. Kindly mute yourself. Okay. So because these ligands in the tetrahedron field will not overlap as they are overlapping or they are interacting in the case of the octahedron field. Hence, the energy difference, though the splitting occurs, the splitting energy will be less in tetrahedron when compared to that of the octahedron. So this is the splitting pattern. That is the T2 orbitals. And here the geometry. The octahedron geometry has center of symmetry I. Okay. So we were considering Garrett G. And the tetrahedron geometry do not have the center of symmetry. So we are not considering G in this case. So, and the E orbitals, that is the ones which are oriented, whose lobes are oriented along the Cartesian axis, they are least affected. So they are getting stabilized by minus 6 dq. And then the orbitals whose lobes are in between the Cartesian axis, they are destabilized by 4 dq. And here this energy difference is delta T, and delta T will be less when compared to delta O. Okay. Ligand number is less and orientation of the ligands is different, and the interaction with the orbital lobes is more in the octahedron than in the tetrahedron. Okay. And the energy levels, T2 level here is the higher energy level and E level is the lower energy level. The energy difference is delta T, which is much less when compared to delta O. And in dq wise, the energy difference is called as 10 dq. So tetragonal distortion before going to square planar, that means in between the geometry, like before removing the ligands present in the z-axis, you can know that the z-axis, that is the bond ligand distance, may be lower than the other four or greater than the other four. Such cases are called as the tetragonal distortion cases. This figure is a D8 configuration of the regular octahedron. So when the distortion occurs, either the EG level or the T2G level or both will be split into the various energy levels. Their degeneracy is also lifted. So when the Z ligands are completely removed, then we get the geometry called as the square planar geometry. So this is the square planar geometry where there are no ligands about the z-axis. So this is the splitting pattern. From octahedron, we are studying this because there are no z-axis at all, ligands about the z-axis. The orbitals which contain the z component will be completely stabilized. And many books, they give even the z square coming completely below the this dx and y. Kindly mute yourself. Okay. So this is the splitting pattern. So here the energy difference between the dxy orbital and dx square minus y orbital will be the 10 dq. Okay. All these 10 dq values will be helping you when we are assigning the electronic spectra of the metal complexes, like as you go to the PG level. Next, crystal field stabilization energy. That is the energy difference between this EG and T2G level in octahedron and E and T2 in the tetrahedron, and dx square minus y square and dxy in case of the square planar geometries. That energy difference is called as 10 dq, and that is itself called as the delta O values and delta T values. When the electrons are occupying in these energy levels, there may be reduction in the total energy because some orbitals are stabilized, some are destabilized. Okay. So the decrease in the total energy is termed to be the crystal field stabilization energy. That is the total difference. We will be calculating total energy of that particular species. We will be calculating. Okay. So in the octahedron, it is stabilized by minus 4 dq, and EG levels are destabilized by 6 dq values. So examples, if you take the half filled and completely filled configurations where the electrons are half filled and they are like not paired up, and in D10 case completely the electrons are paired up. If you tally with the energy levels, the total energy will be whatever is the stabilization energy, that will be equal to the destabilization energy, and the total crystal field stabilization energy will be 0. So hence the decrease in the energy caused by the splitting of these energy levels is called as crystal field stabilization energy. And this crystal field stabilization energy, it is occurring because of the approach of the ligands. So in some of the textbooks, they may mention even as ligand field stabilization energy. So don't get confused. Both are one and the same. Okay. So octahedral configuration, you can write in terms of the electrons present in T2G level and electrons present in the EG level. So net configuration can be given in terms of this, the X, where X is the number of electrons present in T2G level and Y is the number of electrons present in the EG level. Okay, so here we will be talking about the weak field and strong field. This more about it you will be understanding when we study the spectrochemical series. Weak field is the filling up of the electrons following all this above or Hund's rule. Strong field configurations will be obtained against when the electrons are paired up against the Hund's rule. So where this P is called as the pairing energy. So crystal field stabilization energy, as we all know, it all depends again on the metal characters and the ligand characters. That is the factors affecting this. They change like according to the size of the metal ion, nature of the metal ion, and the ligand surrounded by it. So first, if you consider the metal ion, you can take up the oxidation state. As the oxidation state of the metal ion is increasing, the crystal field stabilization energy increases. When the energy difference increases, the energy between the transition also increases. Then, when the ligands are kept constant, the metal ions can be arranged in this order. See here, the charge also, as the charge is more, the crystal field stabilization energy will be more, and as the charge is coming down, it is also dependent on the size of the metal ion also. then the number of ligands and the geometry. As the number of ligands are more, the crystal field stabilization energy will be more. So delta T will be very, very less when compared to octahedron geometry. So it is almost equal to 4/9 times of the octahedron geometry. Then when the geometry of the metals are held constant, then the splitting of the d orbitals increases with the ligand nature, and that nature of the ligands, that series is called as the spectrochemical series. And the ligands here towards the left side of the series, they are called as weak field ligands. That means these ligands, when they are by forming the bond with the metal, the energy difference between the T2G level and okay, I have muted all. Later I will be removing the muting. Kindly don't worry. Okay. These ligands will split the ligands to a lesser extent when compared to the ligands which are present onto the right hand side. Okay. So the order, it is the halide ions, then the oxygen donors, then the nitrogen donors, and then the highest splitting energy is given by the carbon donor ligands. So here weak field and strong field, I'm giving you example. So this is the D4 system. In the weak field, all the electrons are arranged by having the more spin, and this weak field ligand formation, it is also called as high spin, where the spin of the electrons is maximum. Whereas this Eg electron now is forced because the energy difference is more here. So this electron is getting paired up in the T2G level. When all the T2G level electrons are completely filled, that is 6 electrons total, then only the 7th electron will go to Eg level in this case. Okay. So this strong field, the weak field and strong field, or the high spin or the low spin, will come into picture only after D3 configuration, because up to the total capacity of this tree or the triply degenerate T2G orbitals will be 3 electrons, that is 1 in each. Then only the pairing can occur. So up to the D3, there is no difference between high spin and low spin. The problem or the cases arise only in the cases of from D4 to D7 case. These 4 cases are quite important. When the octahedron geometry is given, you should be careful, and if it is specified whether it is high spin or low spin, while calculating the crystal field energy, there is no problem. If they are not specifying in the exam, you have to calculate the crystal field stabilization energy for both low spin and high spin configurations. So here we are taking the example again of the D4 system, high spin and low spin. So this is the calculation for the high spin, that is this configuration where it is T2G3 and EG1. Now this one electron with 0.6 will be subtracted here. So the energy will be minus 0.6. And whereas here, if you see, all the electrons are there in the T2G level. So the energy here will be, this will be in terms of minus, because it is the stabilization energy. Okay, it should be in minus. Here it is minus 0.6, here it is minus 1.6 delta, because pairing has occurred, plus P we are writing. And next we will see like the other cases also, where the high spin means the spin will be maximum number, and low spin means the unpaired number of electrons will be lesser in number because they get paired up. So energy differences also, you can see the in tetrahedron, it will be the reverse figure opposite of the high spin. And because a tetrahedron, the delta T itself is less, so you need not worry about the strong field and weak field. If they are asking you to calculate, you can do, but otherwise experimentally, in most of the cases, this particular low spin and high spin do not arise in case of tetrahedron geometries. Okay, high spin means maximum number of electrons, low spin means minimum number of electrons, and high spin arises when the weak field ligand is binding to the metal. Low spin complex arises when the strong field ligand is binding to the metal. On these points you should remember. So examples of the cobalt complex, that is with the 6 electrons. Earlier we have taken the example of the 4. Now we'll take the example of the 6 electrons. The cyanide, if you remember the spectrochemical series, it is towards the right side and the strong field, whereas fluoride is a weak field ligand. So this ligand is making the electrons to pair up, and if you observe the energy difference, see how much is the energy difference when compared to the energy difference with the fluoride ligands. It is less. So here pairing is not occurring. So for this, so that means this complex, the cobalt hexacyanide cobaltate 3 complex, it is a low spin complex, whereas this is called as high spin. Low spin, here there is no unpaired spin electron, it will be a diamagnetic species, whereas here you can see 4 unpaired electrons, so it will be a high spin complex. Now, like when you calculate all the energies for the configurations, you can get these values. See here, it is minus dq. All these values are in terms of minus. And here we kept the star because they do not exist generally. Okay, in tetrahedron, you need not bother about the weak field or strong field unless it is mentioned. Okay, whereas in octahedron from D4 to D7, you have to know how the spin, what will be the number of unpaired electrons, what will be the arrangement of the electrons in the high spin and low spin. This is all about the crystal field stabilization energy. And factors affecting also we have seen, that is the nature of the metal ion, geometry we have seen, and then the nature of the ligands. The ligands are arranged in terms of the spectrochemical series, and that series that is obtained from the electronic spectrum, that is absorption values. So that is why it is called as a spectrochemical series. Now the electronic spectra of the metal ions, generally because valence bond theory, that is one of the limitation, the Pauling could not explain, but here there is certain explanation about the electronic spectra. Though the d orbitals are degenerate because of the presence of the ligands, because of the repulsion of the electrons of the d orbit present in the d orbitals and those of the ligands, the d orbitals are split and their degeneracy is lifted. So the transition may be occurring between these d levels, and the transition here in the octahedron may occur between the T2G to EG level. Okay. So because of, see, in the ground state, if one electron is present in the excited state, that electron will be present in the EG level. So because of this electronic transitions, the spectrum will be occurring. See here, this is the titanium spectrum, titanium 3+, where only one d electron is present. So you can see one dd transition. So crystal field theory has explained to certain extent the transitions. And because of these lone pair of electrons, the color also exists. And the lone pair of electrons, or the number of electrons existing, that can be studied in terms of the magnetic measurements. Okay, so the magnetic measurements means when there is the presence of the unpaired electron, the species is called as paramagnetic species. When there are no unpaired electrons, all the electrons are paired up, or there are no electrons at all, then we call it as the diamagnetic species. Okay. And there are the other terms like the ferromagnetic and antiferromagnetic species. So where the distribution of the electrons will be irregular or towards one side only, then we call of different metal ions, we call it as a ferromagnetic species. If two species are there and which are bound to each other, and if their electrons are in the reverse spin, and the resultant becomes the diamagnetic, then we call it as antiferromagnetic. All these points you can just go through some of the books, definitions and all, and the figures you can go through. Okay. And why is this magnetic moment present? Means because the electron generally it spins about itself, and then it will be spinning about the nucleus. So because of its spin angular momentum and the orbital angular momentum, like this, okay, about itself it will be spinning, and about the orbital also it will, because of these two momenta, it will be generating the magnetic field and the spin motion of its own axis. Because of this, we will be getting the magnetic moment. And if the spin of the electron is opposite, and if one is positive and one is negative, then their spins will be cancelled up. So we will see how to calculate from the spin and from the number of like unpaired electrons. Okay, the spin quantum number, total number of spins, if you add up, say 4 unpaired electrons are there, 4 into half plus half plus half plus half, if you add, you get the total spin quantum number. That spin plus or minus half, you label it as ms level, isn't it? So the total spins, when you add up, that quantum number, total spin quantum number, it is designated as the capital S. Okay. So the Bohr magneton, that is the mu value, it is written in terms of, that is 1 by root, means it is the square root. Okay. It is the square root. Whole of the thing here up to here, it is under square. Okay. Then this Bohr magnetons, that is the other cases, like if you write about, substitute all the matter, it will be giving this value. And each electron is having the spin is equal to half. So the spin, total number of spin into n will be giving you the total spin. That is the total number of unpaired electrons, n. If you substitute here, you will be getting the total spin of the molecules. Then the other formula is, this is called as again the spin only formula only. N will be here the number of unpaired electrons. If you know the number of unpaired electrons, you can use this formula, n into n plus 2 under the square root. You can write this formula as like this, under root n into n plus 2. Okay, the power half, it indicates that it is the square root. If you know the number of unpaired electrons, you can also use this formula for calculating the magnetic moment value directly. So for D4, D5, D6 and D7 octahedral cases only, you need to check about the weak field and the strong field cases. Otherwise, and by knowing the magnetic moment value, you can easily predict whether the molecules are high spin or low spin. If the value is less than expected, then it is definitely a high spin molecule, or the strong field, the weak field. If this magnetic moment is there, it is the high spin complex with binding to the weak field ligand. If the magnetic moment value is less when compared to the expected ones, where the unpaired electrons are not present, or if it is a diamagnetic species in certain cases, so then you can expect that the low spin complex has formed, that is, the field strength of the ligand is very, very strong. Okay. So in the tetrahedron complexes, only high spin complexes will be resulting. So this is again the spin only formula. So this is the table. See, these are the number of unpaired electrons. This is the total spin. If one electron is there, half. 2 electrons means half plus half. Total spin will become 1. So 3 electrons, 3 into half, that is 3 by 2, and so on. Okay, if you substitute in any of the equation, okay, under root s, 4s into s plus 1, or even if you substitute into under root n into n plus 2, the value will be the same value. Okay, and experimentally we are getting this particular range. This is the theoretically calculated range, and experimentally you may get slightly this way or that way depending on the ligand field. If all the ligand field is uniform, then the most of the experimental values will be equivalent to the calculated values. But the ligand field nature, each of the ligand may be different from the other. The binding nature may be different. Depending on that, you may be, these experimental values may vary. Okay. So the similar calculations, these are all the like calculations for the 4 and 5. These are based on the high spin values. So similarly, you can even calculate for the low spin complexes. So next, the experimental method, how to measure this is by using the instrument called as Goy Balance. Okay. So this is the Goy Balance, and here these are the strong magnets, and the balance is kept. This is the sample holder. The sample, when you keep first, the empty tube will be taken the weight in the absence and in the presence of the magnetic field. And then you will be placing the sample into it, and its weight is noted again in the absence and in the presence of the magnetic field. Generally, when it is a diamagnetic species, there will not be change in weight in the absence and in the presence of the magnetic field. But the paramagnetic species, the weight will become different when compared in the magnetic field when compared to the absence of the magnetic field. So from those weight differences, you can do the calculations and find out the magnetic moment value. Okay. This setup is called as the Goy balance, which will help us to measure the magnetic susceptibility values by noting down the weight of the sample and weight of the standard and the empty weight, like the empty sample holder weight in the presence and in the absence of the magnetic fields. The next we will see all these properties, how they will be appearing. These are all the electronic levels, T2G level and EG level. This is the low spin complex, and this is the high spin D4 configuration. Okay. So now left side, if you see in the strong field or in the low spin, 2 unpaired electrons are only present, and then in this 4 unpaired electrons are present. Okay. So in this, the delta O is greater than pairing, and here the pairing energy is greater than the delta O value. So Coulombic repulsions and the exchange energy will be present, and the configurations like the magnetic moments, if you see the total spin here, because only 2 unpaired electrons are there, total spin is 1, and whereas in this case, because 4 are there, the total spin, that is capital S value, will be equal to 2. Okay, like this, once you are given the value, you can know the number of unpaired electrons from the standard values, and you can predict whether the complex is high spin or low spin in from the cases from D4 to D7. Other cases will be the same in both the fields. So the placing of the electrons, see from D5, D4 we have seen already in the last slide. So this is the arrangement in the low spin and high spin. You can know here, I have shown here the number of unpaired electrons. Okay. So in D7, if it is low spin, only 1 unpaired electron is there. And if it is high spin, 3 unpaired electrons are there. So there will be massive difference between the magnetic moment values for the high spin and low spin values. Based on this, you can identify whether the complex formed is low spin or high spin complex. See, D8 system, in either cases, both 2 electrons are only present. Same with the D10 and D9 systems. Okay. So you should be able to know the number of unpaired electrons before placing into the formula. Either capital S you are using or N, the number of unpaired electrons you are using. You should know first the number of unpaired electrons to either calculate the total spin or to substitute the value of number of unpaired electron. N in either formula will be giving you the same formula. And because of this presence of the unpaired electrons, the color of this, because of the transitions, the color also will be occurring. And the color it depends on the many factors, that is the number of unpaired electrons, the strength, and then the ligand field strength also. Okay. So these are the various substituents. All are the cobalt complexes, but the variation is there in one of the ligand. Okay. So they are giving different colored complexes. So little exercise we shall also do. We shall fix the ligand and we can predict once this is the already given spectrum, electronic spectrum. Because of the transitions, we are getting the electronic spectrum. Okay. Now this is the absorbed color and these are the observed color which is given out. Okay. Because of these unpaired electrons, you will be getting the colors to the solutions. And then if there are no unpaired electrons, or if they are completely like half filled, where the spin has to be changed, then the color will be very, very light or no color. Okay. So next slide. See, these are all the metal aqua complexes, but they are showing different colors. This first one is ferrous, Fe. Okay. Then this is cobalt. This is nickel, third one. This is copper. And the last one, zinc, because it is D10 complex. The electronic transition cannot occur. There are no unpaired electrons. It is a diamagnetic species. Okay. And water is a weak field ligand. So when the ligand is same, you varying the metal, you will be getting different colors. When the metal is fixed, varying ligands also, they also produce varied colors to the complexes. Now, how to know whether the complex has formed? Okay, there are certain parameters with which you can identify that the complex is formed. So example, change in the chemical property. This change in the chemical property, I think in the first class, in the first introduction of the double salt only, we have seen the species, once the complex is formed, they lose their identity and they will not give the semi-micro tests. So examples, Here, ferricyanide, the 6 should be the subscript and 3 should be the superscript. Okay. So these cyanide ions or the iron ion will not give the group 3 test because it is not an independent unit. And this hexacyanide-ferrate 3 is acting as a single unit. Okay. And here for this diamine argentate complex, here this complex will silver, that is the chloride ion, when you add, it will not be able to precipitate the silver present inside the coordination sphere. If you add the nitric acid, then the coordination sphere breaks and ammonia is liberated. Then if you add the chloride ion, it will give precipitate. But as far as this silver is bound to ammonia in the form of a complex, the chloride will not give the silver chloride white colored precipitate. Okay, that means there is a property change in the metal ions or the ligands. Even ammonia will not give it will not give the brown colored precipitate when you add the Nessler's reagent. The species lose their identity and whole coordination sphere acts as a single entity. Okay. Then next we'll see the color changes. The color may be changed from the aqua complex. When any metal ion is dissolved in water, it forms the aqua complex. When other ligation ligands are adding, and when this water is being replaced, then the complex formation can be identified by the change in the color. For example, this is the copper. Aqua complex is blue in color. When you are adding ammonia, you can see the dark color where it is forming. Some of the water molecules are substituted by the ligands. Okay. Now the ammonia molecules are replacing the water molecules. And then next parameter is the solubility change. The solubility of the sparingly soluble salt will be increased. Example, if you see this silver cyanide is highly sparingly soluble salt. But when you add potassium cyanide to it, it forms the dicyanide-argentate complex, argentate 1 complex, where this complex is highly soluble. Okay. So this solubility is also varied when it is mixed for when complex is formed. So solubility of the sparingly soluble salt like silver cyanide can be increased by adding the KCN. So for this, many examples will be there in your textbook. You can go through, and this complex is more soluble when compared to the silver cyanide salt. The next, conductivity measurements. Conductivity measurements may either be increased or decreased. It depends on the reactants and the products formed. If earlier your reactants are the charged species and the complex formed is having less charged, see, the conductance is because of the mobility of the ions. When the mobile ions are decreased, then conductivity decreases. So that also is an indication of the complex. Or if the neutral species are forming a complex and complex is having a charge, then the conductivity may increase. So we can see examples for that. This is given in your textbook. Okay, these two species are now the neutral species, but when the complex is formed, see the complex and the hydrogen ions are liberated. These are more mobile in the solution. So the conductivity of the solution after the formation of the complex increases. And see this here, the aqua complex of copper is charged, acetate ion is charged, but on the formation of the complex, here the glycinato complex, the charge over the complex ion is 0, so the conductivity decreases. So conductivity may increase or decrease, but change in the conductance value will predict the formation of the complex. And to the last, you can discuss the pH value. And we consider all these metal ions to be the Lewis acceptors and the ligands to be Lewis donor atoms, isn't it? When this metal is binding to the ligand, what happens? This ligand protons may be released into the solution. When the protons are released into the solution, when H plus ion concentration increases, what happens? The pH value comes down. That means the acidity is being increased. There will be drop in the pH value. So when the complex is formed. So these are the parameters which you can write to know, to identify that the complex is being formed. Okay. Next, the stability of the metal complex formed. So the equilibriums, for many of the equations, we have seen the equilibrium studies, equilibriums, and before, like the tetrahedron complex or square planar complex is formed, or the octahedron complex is formed, the number of ligands, you know, it all depends on the coordination number of the metal ions and the nature of the metal and nature of the ligand species. And the complex formation may occur like all the ligands may bind to the metal ion together at a time, or one after the other may be bound. And once the metal ion is dissolved in water, we all know the aqua complexes are formed. And the ligands to substitute this water molecule, that means the affinity of the ligand should be there for the substitution. So that means the ligand which is leaving should be faster enough. That means in terms of the kinetic stabilities, we call the ligands which are replaceable faster, they are called as the labile species. Okay. And which are not, or which are very slowly substituted, they are called as the inert complexes or substituted ligands. So that is in terms of the kinetics. In terms of the thermodynamics, we can talk in terms of stability constants. That is the equilibrium constant or the formation constant of the metal complex. So this again, the stability constants will be of two types: stepwise stability constant, where one by one ligand will be binding, whereas in the overall, all the ligands will bind to the metal ion at the same time. So here copper ion is binding to one ammonia molecule, forming this mono ammonia copper 2 species. Then to this mono ammonia copper 2 species, you can add one more ammonia. It is giving diamine copper 2 species. Then diamine species, if you add third molecule of the ammonia, triamine species is formed, and so on. And this at every position, the equilibrium constant, you all know, it is the concentration of the react product divided by the concentration of the products. Okay. And this equilibrium constant can be given in terms of K1, K2, K3 and K4. And the values of K1 will be very higher when compared to K2 and so on, because in the beginning, the first ligand has more probability of holding to the ligand. As the ligand number is increasing, the further incoming ligand will find some inertness of binding to the metal ion. So the stability constants also, they will be in the order of K1 will be higher than K2, than K3, and K4 will be the least, and so on. And we'll see the overall stability constant here. The instead of the 6, the copper will be binding only to the 4 ligands. So like this, all the 4 ammonia molecules will be binding, and this type of the formation, it is here, it is shown as Kf, or we can call it as beta. Beta will be the overall stability constant. Okay. So this is the product and then reactants, and this will be equal to K1 into K2 into K3 into K4. So that derivation you can just go through your textbook. Okay. And this when you write in terms of the log. So how many Ks are there? Beta will be that number. Now here 4 stability constants are there means I will be just writing and showing. It will be the overall stability constant will be in terms of the beta. I'll write here. It will be in terms of beta 4 will be equal to K1 into K2 into K3 into K4. And in terms of the log, you have to add up. Log K1 plus log K2 plus and so on. Okay. Then we have the methods like how to know the composition of the complex formed, whether it is ML6 or ML4, ML2 or ML. It all depends on the ligands, isn't it? We have seen the various dentate ligands, bidentate ligand, tridentate, hexadentate like EDTA. So EDTA, when it is hexadentate, when it is binding to metal, it always form only 1:1 metal ligand complex. If the monodentate ligand is forming, like in the, it may form ML6. EDTA will be forming ML only. Okay. And then we may be having, if it is a bidentate ligand, maybe like ethylene diamine for forming the octahedron complex, it may be like ML3 type of the complex. So to know whether what type of the complex is being formed, 2 methods are, we'll be studying. Actually 3 methods are there, but only 2 methods are there in your syllabus. That is Jobs method, mole ratio method, and another one is the slope ratio method is there. So here in the Jobs method, we will be preparing, you have to take the fixed concentration of the metal ions. Okay. Metal ion concentration, say I say X molar. Okay. This may be the stock solution. And ligand also will have certain concentration of the stock solution. From this, what you will be doing is, you will be preparing a series of solutions. These are the number I am writing. Okay. So you are going on changing the mole ratio of both the metal and ligand. Say metal, if you are adding here 0 ml, you will be adding 1 ml, 2 ml, 3 ml, 4, 5, 6, 7 ml and so on. And the ligand will be again in the reverse direction. Okay. So from this side you can start, the ligand may be 0. Okay. 1 ml, 2, 3, 4, 5, 6 and 7. So if you see the concentrations, because they are fixed, the total concentration of the metal plus ligand has been a constant value, but the ligand is varying and the metal is varying. So colored solutions will also vary, isn't it? So take whatever is the solvent, you can use that as the blank, and then you can measure the spectrochemical or the OD values to all the solutions. And if you plot the graph, you will be getting an inflection where that mole ratio will be predicted. Is it 1:1 or 1:2 can be predicted. Okay. So the method, you should know here the total number of moles of the metal and the ligand are considered to be constant. Both will be varied, but total will be constant. And then the solutions, you can calculate the mole ratio with these formulas, and then you can plot a graph, note the absorbance values. See here like this, the colors will be varied. The one which is showing the darkest color will be the composition of the complex formed. Here, this is the example of iron and Ofin complex, ferrous and Ofin complex by the Jobs method. So you should know what is mole ratio. You should know how to prepare the solutions. You should know how to operate the spectrophotometer, or you can do the experiment even in colorimeter also. Okay. So from the plot, you can know based on the mole ratio, what is the, here it is some 0.75 is formed, and iron and Ofin, it is forming 1:3 complex. Ofin, orthophenanthrolene, is a bidentate ligand. It forms three ligands are binding, forming the octahedron complex with ferrous ion. Okay. So the next method, or the alternative method for this Jobs method, is the mole ratio method. In this mole ratio method, either metal or ligand, you will be keeping it at fixed composition. So earlier what we have done, we have changed in the 1, 2, 3, 4, 5, 6, 7 solutions. When we are taking the number of solutions, the metal ion solution, or say you will be uniformly adding one concentration, you will be fixing. Then you can go on changing the ligand concentration, 6, 7, and so on. Okay. So here one is fixed, the other is changed, and you will be making the volume equal by adding water or any other solvent, whatever it is required. And then the same procedure is followed. The OD values are taken for each of the solution, and then you will be plotting the graph like this. If it is ml graph, you will be getting at 1 mole ratio, 1:2. If it is 2, both are forming in certain complexes, both may be shown. So 2 inflections you may be finding. Okay. So these two methods are very, very important to know the composition of the complex formed. Okay. This is with M 1:1, this is 1:2, and it is both one after the other, stepwise 1:1 and 1:2 formation. Then we come to the application part of the coordination compounds. We have studied to 4 theories. Okay. In each theory, like the predictions, postulates, you should remember. Werner has spoken about the secondary and the primary valencies, and then Sidgwick has spoken about the effective atomic number, and then the Pauling has talked about the hybridization and the magnetic moment values, and then but the limitation was any of one should be known to us. But here in the crystal field theory, the bonding was predicted as the ionic bonding. To certain extent, they were able to predict why certain, like inner orbital, outer orbital. If you see in the valence bond theory, now you will be understanding. That means in the crystal field theory, the ligands were classified into high field or the strong field and the weak field ligand. That means when there is a strong field ligand, the pairing up is occurring. That means inner orbital complex will be formed in valence bond theory. But that prediction was not given at the time of the Pauling, but we can understand after you study the crystal field theory. Okay. So now we will see applications of the coordination compounds. So various applications are there in the field of like medicine and in the analysis. In every field, you can find our human body, our hemoglobin itself is the complex formed with the iron and the heme proteins. Then we have the nature in nature, the phenomena which our trees will follow photosynthesis. The chlorophyll contains the coordination compound with magnesium. Okay. So let us check out with the applications. Let us see how it is helping in the analytical chemistry. In certain cases, it is for the qualitative analysis. For copper, if you see, if you add ammonia, what is happening? It is forming a dark blue color solution. you can identify. Okay, that is like qualitative analysis. Here the quantitative analysis, nickel, you all know, right? It gives red colored precipitate with dimethyl glyoxime, which you can separate it by filtration in gravimetry, and by the weight of the complex formed, you can know the amount of the nickel. Okay, so this helps in the analytical chemistry in the quantitative and in the separation of the mixtures, cobalt from the nickel. Okay, and the separation of the ions in the solvent extraction. Dithiazone lead ion, 2+ ion, it will be in the aqueous medium. Dithiazone, it is a neutral ligand. It can be, it will not be soluble in water. It will be soluble in the immiscible solvent, say a chloroform. You can mix it and you can take it in the separating funnel and you can just go on shaking. Then what happens? This dithiazone has affinity to bind to the lead, which is charged species. And then once the complex is formed, what happens? The complex will come into the organic solvent being neutral in nature, because the ligand, some of the proton will be replaced by this lead ions. Then the neutral complex will come into the organic solvent, and then you can separate the lead, or you can extract lead from aqueous layer in the form of lead dithiazone complex. Okay. Then next, it can be used by forming the chelates. We have studied in the last class what is a chelate, what is the chelation, isn't it? The chelates are the ring forming structures. Okay, the chelates are the ring forming, and the formation of the ring is called as the chelation. Okay, so say for example, the same case of the lead poisoning in terms of the children. Generally in the olden days, the wooden toys which were like painted and all, or some of the painted toys, if the children keep in their mouth and play, the lead poisoning should occur, and then the lead can be, it is very dangerous and it can be removed out of the body by injecting EDTA. EDTA is a hexadentate chelating agent. It forms 5 rings with a metal ion and which forms a soluble complex so that it can be thrown out of the body through excretion. Okay, so lead and calcium can be removed here with the chelating agent EDTA, and then the excess of the copper accumulated in the liver also gives the diseases for the central nervous system. Even this can be removed by the same EDTA. Injecting through EDTA, and then it comes, because it is forming a soluble complex, it comes out through urine. And penicillamine for the copper poisoning. Okay. Then metal chelates, again in the living system, we have discussed the hemoglobin, the mammals, it acts as an oxygen carrier. This one. So 4 moles of it will be binding to the iron atom, forming the hemoglobin. Okay, globulins. And then the chlorophyll. So it is such a big molecule here. See the centrally present magnesium ion. This is called a corrin ring, whereas hemoglobin, it is a porphyrin ring. This is also porphyrin type only, with some minor differences in these peripherals. Okay, so all the plants, they take up carbon dioxide and they liberate oxygen with the process of the photosynthesis. Okay, so this central metal ion is magnesium in this. And then the catalyst, many metal ions, they are the complexes, they act as the catalyst. Here the Ziegler-Natta is the catalyst which helps in the formation of the polymerization of the polyethylene or polypropylene and so on. So this is like a combination of the metal salts used earlier, but later it is known that through the combination of these, the titanium chloride is the major species which is responsible for the polymerization, like different mechanisms. Though it is not there in the syllabus, just for your knowledge, I got this. And here you can see this metal, it is adding on to the alkene. Okay. So the mechanism of the Ziegler-Natta polymerization, it involves alkene binding and the insertion of the species and the chain expansion. The next example in the, again in the medicine, like gold and silver products are also used in the medicine. Here we are talking about the gadolinium-3. All of you know what is MRI. Normal MRI is different than sometimes they'll be injecting a dye to do the MRIs. When the normal MRI, they are unable to predict the results properly. The proton NMR, you know, the water molecules in the body or in the tissues, they all generate a similar type of the proton NMR peaks. But when there is an abnormality in the cell, there the peak alignments will be completely different. So the abnormal tissues or the any tumors can be identified. So this gadolinium, when it is bound to the DTP, it is like ethylene diamine only. It is diethylene tetra or tetraamine pentaacetic acid. Okay. So this is used into that toxicity and to know the metabol that functioning. See here, the lightening is seen in the MRI. The dye coloration will be coming before you do the MRI when this is injected to the body. So this is the chelating agent DPA, diethylene diamine, like tetraamine pentaacetic acid. So calcium EDTA we have seen, and then we have a complex cisplatin which is used to cure the cancer patients. And then we have the cobalt complex, octacarbonyl complex, which is used in the conversion of olefins to the alcohols. And then the last application, the metaphosphates, sodium metaphosphates are used to remove the hardness of this calcium and magnesium. And then the hardness also can be measured by titration with the EDTA. Okay. And calcium and magnesium ions can be separately also studied by varying the indicator. Okay. So with this, we complete the application parts. If you are having any doubts, you can mute yourself and then you can ask the questions. We have seen from the crystal field theory and the applications up to the applications of the coordination compounds we have dealt with. These are all the reference textbooks you can go through. J.D. Lee, then Miss Lorentor, Hohi Keeter and Keeter, and then the Telugu Academy books. In the old okay. Thank you. Thank you for your patient listening.
Thank you, ma'am. Girls, any question you can ask me? You can unmute yourself and you can ask.
Did you all understand everything? because if you understand completely or if you don't understand anything, the questions will not be there. Is the lecture clear to you all?
Yes, ma'am. Yes, ma'am.
Yes, for what?
It's clear, ma'am.
Okay, okay, okay. So I'll be stopping the sharing.
Jules, you can share your how you have understand or is the lecture clear to you all? You can share your feedback in the chat box. Even I'll share the feedback link.
Ma'am, thank you so much, madam.
Yeah, thank you, Jyoti. Thank you for giving me opportunity to interact with your students.
Ma'am, you covered everything, ma'am, even the second year and final year syllabus.
Yeah, yes, ma'am.
Thank you, ma'am.
Because the final year people, they will be going for the MSc entrance, and this is the major topic for inorganic chemistry, which they'll be getting questions. So it will be helpful for them. So they have to practice a lot.
Applications.
Yeah.
Anjum, you can continue.
Good morning, all. As all good things come to an end, so as this lecture, on behalf of Department of Chemistry, RBVR Women's College, I, Anjum Fatima, Assistant Professor in Chemistry, take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this guest lecture on coordination compounds 2, organized by our department. So at the outset, I thank our guest speaker, Dr. B. Sireesha ma'am. We are really enlightened with your knowledge and presence, ma'am. Ma'am has explained in detail about crystal field theory, the splitting patterns of d orbitals involved in all the octahedral, tetrahedral, and square planar complexes. Ma'am has explained crystal field stabilization energy using weak field and strong field concept in depth. Ma'am has explained the electronic spectra of transition metals and the magnetic measurements, color, and the factors affecting the complex formation. Ma'am, in depth has given the stability constant and the factors affecting the stability, including the stepwise and overall stability with their relationship. So ma'am has explained the determination of complex formation by using both the methods, jobs, as well as mole ratio method. Ma'am has given explanation on application of coordination compounds, even using the medicine, its use in medicines. Thank you, ma'am. Thank you so much. And even I thank our principal, Dr. J. Achita Devi ma'am, for her enthusiastic support. A special thanks to our HOD, Dr. V. Jivanjyoti ma'am, and my heartfelt thanks to our students for active participation. With these warm words and a kind message, we move to the end of this guest lecture. Thank you, ma'am. Thank you so much.
Thank you, Ma. Thank you all the faculty. Thank you. I thank Dr. Jeevan Jyoti, head of the department, and the principal of the Reddy College. Thank you for inviting me for the lecture.
Thank you, ma'am.
Thank you, Ma.
Girls, feedback link will be shared to you.
Yeah.